Well, thank you and welcome. My name is Donevan Dolby, as Alex said. I work for Base 2 Solutions. For the last couple years, my team and I have been working on a diagnostics application for the Boeing 737. This application is similar to the software that drives your check engine light in your car. So when that light pops on, you need to do something to it. Similar idea with the Boeing 737. This code has been developed over 2 years. It's grown to about 16,000 lines of Clojure code, making it one of the largest code bases out there in Clojure. So I'll go over a little background of the Boeing 737 program, how our software is designed to work, kind of the approach we took, why we picked Clojure, some challenges we faced along the way, some lessons learned, and then finally how the project was received, how it's operating, and then if we were to do it all over again, would we actually pick Clojure to do that? So Boeing's been working on making a more fuel-efficient Boeing 737. It's, the next iteration is the MAX. To meet these efficiencies, they've added new components. A couple of those new components are new engines. These new components bring with them new sensors. And these sensors are really a technology disruption to the traditional way that the mechanics and technicians interface with these sensors. This aircraft is going to go into service next year. It's had its first flight a couple months ago. You may have seen it on the news. Base 2 was brought in to try and address this technology disruption. We have done quite a bit of work in highly regulated spaces. We're a software development shop consulting. So it's kind of how we got to start here. So a little background on the traditional way that the mechanics and technicians interface with the sensors. They first have to physically locate them, which I don't know if you can kind of see on here. There's actually a little bay here. This is in the belly of the aircraft, and these are all the sensors, and they actually have to climb up in here. And on the back of each of these sensors, there are little screens, and they have to read those screens and then go look up in a manual and maybe do some calculations manually to determine what's actually, if there's any maintenance required on the aircraft. It's a very manual process. And now going forward with the new components, the new sensors that come with those components no longer have that display on the back, so they can't actually do this manual process anymore. So our software, which is called the Onboard Maintenance Function, or OMF, is really how to handle this technology disruption. And it's really a disruption during both manufacturing and maintenance of the aircraft. During manufacturing of the aircraft, they'll be installing components and they need to run diagnostics on it. So the OMF really will consume all the sensor data and will run any calculations and then display to the end user, in this case technicians or mechanics, the maintenance messages. There are over 6,000 potential maintenance messages that can be displayed, so a bit more than in your car, for sure. And so a way to efficiently show this to the end user really is important. So during manufacturing, they're installing new components. It takes a few days to do this, and as they're running through that installation, they're running diagnostics tests on there. The OMF solution will be part of that. They can run tests, they can get sensor information as they're installing this. It's our hope and Boeing's hope that this new process is more efficient than the current manual way of doing that. And as it's more efficient, it should make producing these aircraft faster, which with over 3,000 orders of the aircraft, it's important to get these all out. I don't remember the exact number, how many they can do a month, but it's, on the order of 20 or 30 a month. So it's going to take a long time to fill all these orders. Beyond manufacturing, there is a maintenance component. The airlines are really asking for improvements at gate turn. So gate turn is boarding and deplaning of passengers, servicing, loading and unloading of luggage, servicing of the laboratories and stuff like that. But there's also a maintenance component. This is important to get these times down because the 737 is used for short-haul carriers, so these are flights that last less than 3 hours typically. If you're in the air for 3 hours but then on the ground for an hour or more, that's 25% of your operating cost. So airlines really have a big interest in getting these times down. And also it allows them to get their flights out on time, which makes passengers much happier. Again, the new process should be more efficient, so we'll have a direct effect on this maintenance check. So at every gate turn, the technicians board the aircraft and view all these messages. So a little history. Starting with the 787, Boeing had this E-enabling initiative where they want to connect the whole aircraft. And as part of that, they added a piece of hardware that consumes all the sensors and does basically what OMF does. Unfortunately, it's a huge piece of hardware that doesn't fit on the 737. The 737 is a much smaller aircraft. Fortunately, the predecessor to the MAX, the next generation, or NG, added a component called the Onboard network system. And this connected all the components, but it actually doesn't do any of these calculations. So the OMF product is designed to run on the ONS platform. It will consume the sensor data, run it through these 6,000 fault evaluations, and then expose that through some REST interfaces. There's a few different ways that the sensor data or that the information can be displayed. There's a couple screens in the cockpit and our flight deck that the maintenance technicians can use, and they can also just plug in a laptop or use their iPads to view this. And so we used REST to expose all that. And then there's also some communication that can happen during the flight. We can trigger events, or ground systems can actually request information, and it'll be sent to these ground stations over satellite or cellular transmission. So initially, Boeing came to us with the 787 solution, the language that's defined, used to define the maintenance messages, and asked if we could create a software solution that does that. So parse this DSL and see if we can simulate sending sensor data through and evaluate these faults. And once we proved we could do that, Boeing awarded us with the contract, which comprised of over 1,700 requirements that define what a fully functional OMF system really should be. And it covers things like how do you determine what a fault is, and that's really the domain-specific language. Basically checking that sensor values are within certain parameters, and if they're not, then it indicates a fault. It talks about how to determine what a flight phase is. A flight phase is like your taxi in, taxi out, takeoff, cruise, descend, land, that kind of thing. Those are also determined using the same domain-specific language. So there's sensors all over the aircraft, check the weight on wheels, can see if the doors are open, that kind of thing. And so we use those to determine what flight phase we're in. And then flight leg is when you board the aircraft and they close the doors, and then you take off and you land at your destination. Again, those are also calculated using the domain-specific language. And then we have things actually communicating directly with the sensor to command them to do things. When they're installing components, they really need to know what firmware is installed on this software or on the sensors. And so we have to understand how to actually send and receive messages from the sensors in that regard. They're also running diagnostics testing to make sure the sensors are working properly. And so we've got requirements around that. I think I mentioned before, there's reporting requirements, so how they get information off the aircraft for analysis at later times. Then we had some performance and data retention type of requirements, and so they kind of bucket that into our database management. And then Boeing really needed a way to actually define these maintenance messages and configure the system, so they needed a configuration tool. And so we have some requirements around that. And then we really have this derived requirements that I'm calling input simulation. When we started developing this, the system that we get the sensor data from was not complete. So we couldn't rely on it to run any testing. Also, we needed to verify that our fault processing or logic evaluation is actually working properly. So we needed to know exactly what inputs were coming into our system, and so that we know that our equations were evaluating properly. So here's kind of an overview of the functional areas in our system. Down at the bottom, we have our persistent service. We use SQLite as our database. We needed some relational database capabilities, but we didn't need a database that has the overhead of, say, Oracle. It needed to be something that doesn't require any administration on it. This is running on an aircraft that has no way to really interface with the database itself. It also needed to be lightweight, where you have a pretty small system that we're running on, so not a lot of hardware to grow there. The ADS service, The ADS service is how we communicate with the sensors and get the sensor data. The MEF service is how we communicate off the aircraft, so when we're sending over cellular or satellite communications. Building on that, we have our fault processing, and then we have this messaging service, and then the higher levels, we have our services to calculate flight phase, flight legs, ground testing, that kind of thing. And at the top, we have our REST interface that really reaches into all these different areas to expose information to the UIs. So why did we pick Clojure? So we knew once we had the prototype, we knew we were going to have an event-driven type system. We're going to have users clicking buttons, interacting with our system. We're also going to have sensor data coming into our system. Because of that, we really wanted to use a functional reactive paradigm. And that kind of eliminates a lot of the imperative languages, really feels like a functional language type of implementation. We also had a DSL we needed to parse. Lisp has a long history of natural language processing. Clojure is a Lisp syntax language, so it seemed like there might be a natural fit there. Also, early on, we found Instaparse, which providing it a BNF was very easy to actually parse the syntax, and then mapping those trees to actual functions to evaluate them, much easier in a functional language than, say, using Antler with Java. There was also parallelism that we thought might be there. We have over 6,000 faults. We're going to be running the same sensor data across all 6,000 faults. Seemed like there might be some opportunities to take advantage of parallel processing. Turns out we didn't actually use that. The syntax allowed some dependencies between equations, so some equations might refer to others. And trying to build that dependency hierarchy would add a bit of complexity to our engine, and we didn't need the performance. We were able to keep up without doing this in parallel. So we ultimately didn't need that. Then I mentioned before, there's no capacity for new hardware. We couldn't just reuse what was done for the 787. We needed to run an existing configuration, which was the ONS, and that ONS had a bunch of Java apps on it already, so there was already a JVM. So we take that all into consideration. Clojure felt like a good match there. Okay, so now that we've picked Clojure and we've started development, I'll go over a couple challenges we faced. The first one related to dependencies. As I showed you here earlier, all these lines really represent some dependencies, and this isn't complete. This is really just notional. Trying to write this programmatically when you got developers developing different components in parallel, trying to manage a startup and shutdown sequence, like one function to do that can be pretty challenging. And even if you get that all right first time, now you have to go back and fix some bug, and you find you have some new dependency between some components. Now you have to go maintain that startup and shutdown sequence. So there's lots of places to introduce problems there. We found Trapper Keeper pretty early on. Trapper Keeper allowed us to define each of these components as services, Trapper Keeper services. And as part of that definition, we can specify what other services we depend on. So I have some code here from one of our flight phase service and all the dependencies it has. Then we were able to tell Trapper Keeper, okay, on startup, we want you to start up all these services. And then Trapper Keeper is able to go through, find all these specifications there, and then build its own dependency hierarchy and start up your application in the proper order. So another issue related to dependencies that we ran into was circular dependencies. We have, on the left, we've got this fault engine, which evaluates our logic equation language. And one of the things that can be specified in that language is checking what the current flight phase is. So I have an example equation here. We're looking at the presence of some sensor data and that the current flight phase is actually taxi in. So that kind of implies that our fault engine needs to reach out to the flight phase service and get some information, so import some functionality to get the current flight phase. But our flight phase also uses the logic expression evaluation to determine what current flight phase is. And so that really implies that we need to register those equations to be evaluated with the logic equation evaluator. If we do this by importing functions from flight phase and then flight phase importing functions from fault engine, your code will not run. It won't even build. So how do we meet these requirements of the language, but also adhere to the language constraints? So what we did is we added a messaging service in the middle. So our flight phase service still continues to register its equations. But instead of the fault engine going back to the flight phase service, it will request a subscription from the messaging service for messages related to phase changes. And after it gets the phase change information, then you can use that as its current flight phase and evaluate the expressions. And once it's done that, it will then publish out to the messaging service any changes to any of the logic equations. So anything that goes from active to not active or not active to active. Then over in the flight phase service, we will create a subscription for any changes to the logic equations and filter it even more down to just the logic equations that we've registered with the fault engine. Once it gets all that information, it can then calculate what the current flight phase is, and then it can publish out a message out to the messaging service saying that this is the current flight phase. So now there's not a reach back into the other service. We've broken the circular dependency, and we're still meeting the requirement of evaluating the syntax. So I'll dive a little bit into the messaging service itself. We built this as a pub-sub framework. It's built using Lamina channels. Lamina is now deprecated, which I'll talk about later. But so basically what we have here on the left are some publishers, a couple publishers, one for the current flight phase and one for logic equations. And at the core, there's one channel. And this channel is a grounded channel, so nothing can accumulate in that channel if there's no consumers. Each time one of these publishes a message into the main channel, it will add some metadata of an event type. So on the top, everything will be tagged with the phase, and on the bottom, everything will be tagged with the logic. And then our subscribers, what we do there is when a subscription is requested, the master channel is tapped. So basically, it gets a copy of everything that goes into that master channel. And then we apply a filter to that that will just filter on the event type, matching the type that we're interested in. And down here is pretty much the extent of the code. So it's pretty small. We have the master channel, and we have a publish function, which takes an event type and then the event, and that just enqueues it into the master channel. And then down in the subscription, we tap the channel, and then we apply a filter, and we only look for messages that have that message type in it. All right, go over some lessons learned. First, performance. It's been a couple years in development. We've had a few iterations of performance improvement and tuning over that time. Clojure runs on the JVM. We picked YourKit as our CPU and memory profiling tool, since it's a JVM tool as well. Primary offenders have been memory leaks, so our system has to stay up for like 7 days, which doesn't sound very long, but we have a very small system that we're confined to. So any type of small leak becomes a problem after a few days. The vast majority of our memory leak problems have been improper use of Lamina channels, so not grounding a channel and having producers so it continues to grow. Or we've had channels that had consumers, but then the consumer went away and didn't close the producer, so it just keeps accumulating messages. One thing I would say is it's probably the case with any of the CPU memory profiling. The way that Clojure objects, persistent data structures, are mapped to Java objects, it can become challenging to backtrack who actually still owns that object, like why is it still alive, why hasn't been garbage collected. Just a quick example of some YourKit output. Just recently, we fixed a problem in our mock service, or our input simulator service. Every time we'd restart our OMF service, our input simulator the memory would jump up and it would never recoup. So you'd restart half a dozen times, then it would ultimately crash. Turns out it was, again, a misuse of Lamina channels. We were connecting a couple channels, and in that connection, you can specify if the source closes, close the destination, or if the destination closes, close the source. And we had that reversed. And so when we lost connection to from OMF, it was closing like half our channels, but the rest of them were still remaining open. It was pretty difficult to find. But after that, then we can see, so here, the orange is old gen memory that can't be garbage collected. And down here was after that fix. So it's pretty dramatic change there. All right, so after we kind of exhausted our use of YourKit and we still were having some performance issues, we raised our hand and reached out to Cognitech and asked if maybe they can come in and analyze our code, look at our code, do some code reviews, see if we're doing anything systemic, like nothing terribly inefficient, but maybe lots of the same pattern that has mildly inefficient things in it. So a couple of things that we took away from that was one, we should really move from 1.6 to 1.7 and now 1.8. And 1.6 to 1.7 introduced transducers. A transducer, I like to look at what it means in the real world. So if you look at what a transducer really is, an amplifier is a transducer. So an amplifier takes one signal, applies an external source of energy to it, and it boosts that signal. Transducers in Clojure are similar. You take in a collection, you're doing something to that collection, and you have a new collection that comes out the other end. You can do this here where I have a collection on one side and we're adding a bunch of shapes to it. You can do this in Clojure 1.6 or before 1.7 using, we had a bunch of these where we were threading a collection through a bunch of a sequence of maps. And so you can get the same behavior, but that adds on each one of the iterations through the map. After each map, we're stuck with a temporary persistent data structure, something that nothing's ever going to use. So there's really no reason for it to be persistent. Transducers bypass that persistent data structure, so you don't have to take on the overhead of every step of the way, keeping track of the persistent data structures. We had a fair amount of this pattern where we were threading data and manipulating the data structures, and so changing over transducers definitely improved our performance. The other area, the other takeaway is we don't need to be purely Clojure. Like, we should be using the right tool for the right job, right? We have an input queue, an event queue, where all our data is coming in. It's one producer, one consumer. We're not trying to make this parallel. But when we first implemented it, we kind of had this event queue. The structure, the data structure storing that was just a persistent queue. But that brings with it, as the name implies, persistent data structures. But since this is not shared and not spread across multiple threads, there's really no reason to do that. So we just switched to concurrent linked queue, going to Java directly. We did see a significant performance improvement there. And it was part of our main processing loop of fault processing, so that's an important place to get improvements. All right. Next thing I want to talk about is library selection. So Clojure is still a pretty young language, and as such, a lot of its libraries are still young and somewhat volatile. Lamina, for example, now is deprecated. We found that out about halfway through our development after we really fully adopted and embraced Lamina as our messaging protocol. Other things I want new developers and a new community. It's kind of hard to find some libraries and to know that maybe there's a library that does something that you want. We have a fair amount of SQL just embedded as strings within our Clojure code. If we'd have known about YesSQL or HugSQL, we probably would have done some research to see if that made sense to maintain that through one of those libraries. And then our reports we have that we regenerate, we use mustache templates. Early on, we selected Clostash as our mustache rendering, and it worked fine early on. We didn't need, functionally it was great, it was easy to use, but we didn't need performance we didn't think. This wasn't something that had to happen in real time. It was more event-driven, could take a while. Turns out after the aircraft has been on the factory floor for 7 days and they've been toggling on and off sensors and creating thousands, tens of thousands of faults, maybe hundreds of thousands, Clostash, when it tried to render these reports, it just couldn't keep up. I think under the covers it's using some regex, and when you're dealing with huge files, it just doesn't perform. Fortunately, we found Stencil, which is another mustache library, and we were able to swap out the couple places. So we have a dozen or more report types. We just swapped out the two that were really big offenders. So the takeaway really is to wrap your libraries. Like if you're going to adopt a third-party library, you should really put an abstraction layer around it to really isolate yourself. Our mustache was pretty good. Each report actually had it pretty encapsulated. It would have been better if it was one place, but only having to change a couple places really isolated any regressions. Lamina, on the other hand, is pervasive throughout our code. It's all over the place. So switching to core async will be a massive change if we have to do that, both from a coding effort, but also from it's going to introduce regressions, and so trying to work through all that will be pretty challenging. Right, and then there's kind of a learning curve for new developers. The majority of developers out there are still coming from an object-oriented background. So dealing with collections and iterating over collections, they understand for while loops. But, trying to think of your collections and iterating over them into maps and reduces, it's definitely a paradigm shift. And the other thing is really immutable state. Like, what does that even mean? Like, when you're coming from an object-oriented program, like, what do you mean I can't change this object? How am I supposed to do what I need to do? You get them over that hurdle, and then it's understanding how they do it in Clojure with persistent data structures, and what does that mean for my performance. Fortunately, we've had pretty good success when we bring in a new developer and we pair them with a veteran on the program for about a week or two. They become very productive right away. And even early on, kind of the original members, none of us were using Clojure before, and we did a lot of pairing together, and we learned a lot. So it certainly was very beneficial to overcome that. All right, so the product is actually out there now on the factory floor. Customer's very happy. It's been on a couple flights. It's fantastic to be on a project that has actually been delivered. I don't know. I don't think I'm alone when I'm on a software project that just doesn't ever see the light of day. It's kind of nice to actually be on something that gets delivered and actually works. A little bit about the development process. We found this or at least I did, I'm sure others did. Clojure is so concise. It makes merge requests and code reviews not enjoyable, but much more enjoyable than in other languages. You can do them in 20, 30 minutes as opposed to 2 hours for the most part. Also, I imagine if we had written this in C++ or Java, we would be looking at 2 to 3, 4 times the size of code base, so much bigger code base, much bigger effort. Unit testing is much easier in a functional language, and Clojure's functions for allowing you to unit test really encourages that, so it's encouraging best practices, which is great. At one point, we had Cloverage running, and we had really high code coverage, but our project grew so large. At some point, I don't remember which library was introduced, but one of those libraries actually broke Cloverage, so I don't know what our code coverage is anymore at this point. Yeah, so that's that. So would we still use Clojure? And I would say yes, with a couple exceptions. So our input simulator, our mock service, we implemented using Clojure. There's really no technical advantage to using Clojure. It's just a REST endpoint that's simulating canned data or generating random data. Could have easily been implemented with Node.js or Python or something else. And we could have taken the Clojure resources that were implementing that and put them on the core application, the core OMF functionality. Also, we have some functional areas, in particularly the ground test, where the implementation of that, which I have to take some credit for, not in a good way, it really feels object-oriented. There's lots of maps and references, atoms and references that were mutating, and the design feels very OO. So I don't know if OO would be better, but the way that was designed and implemented, doing it in Java probably would have made more sense at this point. All right, before I take any questions, I want to recognize a couple people. This project did take a team. A couple of the team members are here. Tim Clemens is one of the founding members of OMF, and Jason Racy over there. He just joined us a couple months ago. He's the newest member on OMF. We have a booth here. We'll be around for the whole show, so if there's any questions we don't get to now, you can come find us. So I'll take questions now, though. Good.
Did you receive much resistance from Boeing for choosing Clojure?
No. Boeing actually has a list of approved languages, and Clojure happens to be on that list, which is surprising, but
I'm guessing there's no way that you
Yeah, they did. Yeah, that's what they did at the gate. Yeah, yeah, yeah. So the question was, basically, there was no way they were doing it at the gate, right? There was no way they were actually checking that, like manual going through that, popping their head up into the bay and reading those. Like it seems kind of crazy that that would be allowed, right, with the regulations. But so one thing I should add is that this is all really related to the performance of the aircraft. None of this stuff is flight critical. So if there's something that's reported incorrectly, or the maintenance crew reads something wrong, it's not going to, they're not putting your lives in danger. Like it's more related to the overall health and performance of the aircraft, not actually keeping it in the air.
I missed how big the code base was.
Code base is over 16,000 lines of code, roughly. Ed? Sorry, maybe we get in the mic. I didn't catch that.
You seem to be doing a lot with engineering math and transliterating engineering math into code. Does it help to be in a functional language when you transliterate math into code?
I think I'll defer that. Let's talk afterwards. I'll have Tim. Tim, if you can come to our booth, we can talk about that later. Good.
You mentioned that you had issues profiling the application. Hello. You mentioned that you had issues profiling the application. Could you speak a bit more how you went from actually looking at the profiling data and identifying the real issues?
Yeah, so the majority of our issues were related to memory leaks. So it was hard to track down these, but basically what we ultimately found is you can see the Lamina objects, these Lamina node objects that get created way down low. And you can fortunately look at the information that's actually in that node. And so really it came down to, we'd see 1 million of these nodes that were in our system, and it's a lot of trial and error of looking at each one of those and seeing, okay, this is a flight phase message, this is a logic message, or this is a ground test message, like finding those. And then if you see a whole bunch of them and you only expect to see a couple of them because it should really be consumed, that's really ultimately how we tracked back. There's only a couple producers of that, so it kind of helped figure out who the actual offender was. It's not that easy, but that's basically where you kind of find the source of it. But it's certainly difficult, like the way that the persistence data structures get mapped, it's pretty hairy in there. Okay.
So I was going to question, did you ever run into a situation in which you have to, say, attack garbage collection, what the application was running, like in mid-flight, or did you have to choose any particular vendor of JVM, like say IBM's or
Yeah, we're using Oracle's JVM. That's the one that's actually on the aircraft, and I forget what's the paradigm we're using for garbage collection. Tim, do you remember? Yeah. It wasn't a big consideration. I don't think we had again, it's not a system that was real time or flight critical. So I don't think we've seen any problems where garbage collection is happening and it's impacting our overall performance. Okay. Any more?
You mentioned that this was a DSL. What does the DSL look like?
Yeah, I have an example of the DSL. So it's not very pretty, but I made it pretty simple here. All right, so the question is, what does the DSL look like? So here's an example. There's an address. Every sensor has an address on it. So it has this 2 digits, DL, and then a number, 014, and then an underscore, and this is called a label. So there's a bus and there's a label, and then there's this thing called an SDI, which is just basically a channel on those buses. And you can specify that can be 0, 1, 2, 3, or X if we don't care. And then this syntax here, we're looking at basically bits 12 through 30, that should be 31. And we're converting that to an unsigned int, and then checking it against this value of 180. And then over here, we have this pres. So there's a couple operators. There's pres, which means present. There's pre, what the previous value was. There's test. There's NCD, which is like do not use. And so that's checking like certain bits on the message, or if the message is present. And then there's this flight phase equals taxiing. So it's looking at the current flight phase is actually taxiing. And very intuitive that O means and. But I didn't show it here, but plus means or, which sort of makes sense. But the O meaning the and, that one's, I don't know.
Did Boeing write the DSL?
Yes. Yeah, Boeing did. Yeah. Good?
Is the communication with the sensor one way? Are you just reading data off, or are you also sending it?
It's two-way. We mostly consume it, but we can command the sensors to run through batteries of tests, and so we send messages to it. Or we can request configuration data, so we send it a request as well. And if anybody's interested, it uses ARINC 429 as the communication protocol, just in case anybody cares. Good.
So you have a large code base. My company, we also have a pretty large code base. I wonder if you could speak a little bit towards Clojure's applicability and any tips and tricks, documentation, training new people. What are the issues that you ran into with a larger code base?
So certainly we ran into, I touched on it a little bit with the Cloverage. Like that was one tool that broke that we just haven't fixed. And then also our ability to run the REPL with our code in it also broke. I think it might have been something with Trapper Keeper possibly. So that makes it a little more challenging to debug because we can't just jump into the REPL to debug it. We have to add print statements or something. Documentation, we're AS 9100 certified, and this is what is called a QMS. I forget what it stands for, but it's highly regulated. So we have a big process. So we have a ton of documentation in there. I don't know that any of it's really useful for developers coming on, like what's actually in the code, but there is a lot of information there. Definitely bringing on new developers. Pairing has been by far the biggest help with overcoming the learning curve of Clojure itself, and then really understanding the code base. I'm sure I could think of more.
What did you use to write tests, and was that regulated in any way?
So we just use the built-in Clojure def test and the assertion checks. It's not regulated. We have requirements that we have to have something like 70% code coverage. So the unit test is really how we test that we have proper code coverage in that sense. But,
With such a large code base, do you have like a refactoring strategy in case you go back and change Lumina to something else?
yeah, we don't let Tim touch the code because he'll want to refactor it. No, we do have some strategies. Like we're investigating right now, moving away from Lamina to say core async. So there's a little bit of an effort going on to see what that actually will involve. There's nothing, necessarily written down for a strategy, but it's just really look to see what it's gonna involve to refactor some code. I guess if you prescribe to the clean coder type of approach, you should always be refactoring your code, right? If your code's not flexible, or if you don't flex your code, your code's not flexible. I don't know if I fully subscribe to that, but there's certainly a community that does. Good.
What's the size of your team roughly?
So it's ramping down now, but at the peak we had, I think, six Clojure devs, 5 quality assurance testers, a couple SDETs, and then some PMs and some. Base 2 also has the whole group of systems engineers, and so we've used them for maintaining like our requirements, things like that. So probably had 15 or more people actually on the project at any one time. Back there? Okay.
How do you find about the state of Clojure tooling?
We're all VI, right? No. Maybe me. Actually, I use Light Table. A few people use Light Table. I think IntelliJ or some. I mean, we're pretty open to whatever tools people want to use for their IDEs. Yeah, there's not really a standard. I would say if I'm working with somebody new, they're probably going to be using Light Table because that's what I use. But they're free to go figure something out themselves. All right, do we have more time for one more, or? All right, one more question.
On a code base that large, did you find any use for schema or type checking, annotation tools?
I think we have a couple places where we do some type checking. Yeah, the REST endpoints, that's exactly right. So REST endpoints, so when we're receiving data requests, we definitely do validation there.
Anything like prismatic schema or core.type or anything like that?
Yeah. Okay. All right, well, thank you.